Astronomy GCSE Topic 12, Formation of Planetary Systems. Now, basically, the first big chunk of Topic 12 is about the effects of gravity in the solar system. There's the obvious effect of gravity, which is that smaller objects orbit bigger objects, planets orbit the sun, moons orbit planets, etc. But then there are other effects of gravity, and that's basically what I'm going to talk about in this video, the effects of gravity on various things in the solar system. So as I said, the first one, gravity keeps smaller bodies in orbit around larger bodies. Because of gravity, the moon orbits the Earth orbits the sun. We say that gravity provides the centripetal force, that's the force towards the centre, required for circular motion. I've already done a video about gravity and orbit in topic 8, and you must have a look at that if you're unsure about this. One important point is that at any particular radius, the smaller body must be travelling at a certain speed. Now, another effect of gravity, how much gravity an object has will determine its shape. And basically, if an object has enough gravity, then it will pull itself into a sphere. Here are some asteroids. The first one is Ceres, which is the biggest asteroid. In fact, it's a dwarf planet in the asteroid belt. And if you look at the diameters of these objects and you look at their shape, then it should also, well, it should be pretty obvious that the more mass it has, the more likely it will pull itself into a sphere. What it's made of will also affect this as well. If it's made of kind of rocky stuff, or if it's something like a comet, comets aren't held together very strongly. But the amount of gravity is very important in determining shape. Tidal gravitational forces. Now, what do I mean by tidal forces? Basically, as you move away from a planet, gravity gets weaker. We say that gravity follows an inverse square law. In other words, if you're twice as far away, the strength of gravity is a quarter. So gravity gets weaker pretty quickly. Now, this means that an object in orbit around a planet, the part that's closer to the planet, the gravity will be stronger. The part that's further away, the gravity will be weaker. And if the difference in gravity is big enough, this will have a kind of a stretching effect on the object, and it will get stretched, and this is going to cause enormous stresses in the smaller body. And here's a fantastic animation of what could happen. The body may start to oscillate like this due to these tidal gravitational forces. It'll cause heating in the body, and the body may break up into pieces. The Roche limit. Now, if the smaller body is just being held together by its own gravity, then the Roche limit is the minimum distance that the smaller body can survive. So if it's further away than the Roche limit, it can stay as an object. If it gets within the Roche limit, then the body will be torn to pieces by this difference in gravitational field strength. So that's what the Roche limit is. And this process is believed to be the origin of ring systems. That's where ring systems like around Saturn come from. I could mention now what happens if you get too close to a black hole, as in you get spaghettified, but it's not on our syllabus, so I'm not going to. The asteroid belt. Okay, now why is the asteroid belt there? Well, all of the other planets were forming, but in that particular region, planets couldn't form very well. And why not? And I reckon it's because of the gravity of Jupiter was disturbing it, so that the little bits of rock couldn't settle into planets because the gravity of Jupiter kind of disturbed the process. And the pieces there had lots and lots of energy, and they were all smashing into each other, breaking up, lots of violent collisions going on, and we ended up with this asteroid belt of lots and lots of bits of rock between Mars and Jupiter. Now, there is a chance that these asteroids banging into each other may actually knock each other out of orbit, and a very large asteroid may end up heading towards Earth. Okay, and there is evidence that this has happened before in the past. Very, very large asteroids hitting our planet. Ask any dinosaur and he or she will tell you that it's bad news. Okay, very large asteroids banging into each other, knocking themselves out of orbit. Potentially hazardous objects they are. Orbital resonance. Now, what's orbital resonance? Now, this is if you've got, let's say, a large asteroid and Jupiter, then what will happen is at certain times they're going to be close to each other, and then the gravity of Jupiter will affect the orbit of the asteroid. And this will obviously happen periodically as they're both going around the sun with different orbital periods, and it's called an orbital resonance. At periodic times, the gravity of the sun and Jupiter will pull in opposite directions on the asteroid. The gravity of planets may affect each other if they're close enough, and in fact this is how now the existence of Neptune was predicted by the effect of its gravity on Uranus. Basically, looking at the orbit of Uranus, at certain points in its orbit, well, at a certain point in its orbit, it appeared to be travelling faster, and then it slowed down again, and it was predicted that a large other planet was affecting its orbit, and that's how it was discovered. Was it Galley and Direct or something? I can't remember. Look it up. Lagrangian points. What's a Lagrangian point? They are parking places in space. There are some very special places. If you look at the orbit of the Earth around the Sun, now the Lagrangian points L1, L2, and 3 and 4 and 5, and it's basically when, let's just look at L1. At this particular orbit, the object is going to feel the gravity of the Sun, and it's going to feel the gravity of Earth, and as a result, what's going to happen is, at the radius of L1, you would assume that its orbit would be faster than it is. But because of the gravity of the Earth, its orbit matches the orbital period of the Earth. So basically, relative to the Earth, it stays in the same place. It's called a Lagrangian point. Okay? An object orbiting the Sun at the radius the same as the L1 point would normally be travelling faster, but because of the Earth's gravity, it slows down its orbit, so relative to the Earth, it stays in the same place. And there's various uses for these orbits. One of them is the SOHO satellite. They've put the SOHO satellite at the L1 point between the Earth and the Sun. And if you think about it, why is that the best place to put the SOHO satellite? And I'm not going to tell you. Think about it. What determines whether a body has an atmosphere or not? That will be determined by how strong its gravity is. If its gravity isn't strong enough to hold on to an atmosphere, then it won't have an atmosphere. It'll depend on the temperature at its surface. The hotter the object is, then the more energy the atmosphere particles will have, and the greater chance there is that they will escape. You know, we talked about escape velocity in another video. And another important factor is the solar wind. If the solar wind is too strong, then any atmosphere would just get blown away. Looking at the pictures, the first one, if we gave our moon an atmosphere, it would lose it. Why? Because its gravity isn't strong enough to hold on to an atmosphere. Mercury hasn't got an atmosphere. It's so close to the sun that the solar wind has just blasted away any kind of atmosphere, and it's very, very hot, so any gas would just escape anyway. And then lastly, Mars. Mars doesn't have a magnetic field like the Earth. If we actually went up to Mars and somehow maybe melted the polar ice caps and gave it an atmosphere, it wouldn't hang on to it very long because of the solar wind. because the Earth has a magnetic field and that protects us from the solar wind. Mars has almost no magnetic field. It would lose its atmosphere. Okay, so there's no point unless somehow we created a magnetic field for Mars or shielded Mars from the solar wind. And there are some possible ways that we could do it, but they wouldn't be cheap. Lastly, the heliosphere. It's mentioned in the syllabus, so let's just make sure you know what it is. Basically, our solar system moves through the galaxy, and as it moves through the galaxy, there's an interstellar plasma of charged particles. Okay, there's like some dusty, charged little particles in the space between galaxies. And as our sun moves through, it's like the bow wave. If you look at the front of the swimmer, that represents our solar system moving through the intergalactic medium. And the edge of the influence of the solar wind, which is what's pushing it outwards, is called the heliosphere. As our sun moves through the galaxy, the solar wind forms a bubble pushing against this plasma, and it goes as far as about the Kuiper belt. It extends the solar wind, the extent of the solar wind, the effect of the solar wind extends into the Kuiper belt. And it's called the heliosphere, the extent of the solar wind.